All right, we're going to start in the immune system now. When we did the cardiovascular, we talked about red blood cells and we learned about what red blood cells primarily do in the body, and now we're going to go into white blood cells primarily. What do you think the human body, why do you think the human body makes such a great place for pathogens to do well inside? Well, for one, our body is an enclosed body. Pathogens will have less exposure to other types of pathogens, which when encountered with each other, they do battle each other quite a bit. They are aggressive toward each other, viral cells against other viral cells. Viral cells love to attack healthy human cells. The inside of the human body, wet, moist, temperature is good. So it's a great environment and it thrives. It does really well. Bacteria, in other words, does real well inside of our body. So obviously they would love the opportunity to go in there. Examples of organisms that cause disease, obviously we spoke about the African tick bird a little bit ago. That's going to cause a disease because if anything, if you get bitten by an organism that has a disease, then that disease is going to spread to you. Some diseases can be environmental in terms of not being spreaded through an actual bite, but rather just simply exposure, like the flu and so forth, airborne viruses, West Nile, things like that. How did disease spread? Well, you have to come into contact. There has to be a contact of some sort, either proximity, as in like breathing the same air as someone who has it, or bodily fluids is also very, very, very common as well. And think about something. Some of you got on board a bus this morning to come to school. You were exposed to 20-something students on that bus. You got off, you got into a class, sat with 20-something students in a class for 2 hours in a less circulated enclosed classroom, breathing the same air they're breathing. Then you go to switch from classroom to classroom and you're surrounded by another 20-something students in the hallways and in lunch. And you do this day in and day out, day after day. And yet we're not sick all of the time. It's because our white blood cells, our immune system, is constantly working to fight off. You do get viral cells that do enter your body every single day. But many of them, your body can fight them off. And so nothing happens. But every once in a while, you'll get this one that catches you at a bad time, or just simply happens to be stronger than your white blood cells. Your white blood cells have nothing in their memory bank that allow them to go back and see, oh yes, I've defeated this one before, you defeat it like this. And so then therefore, that's the one that brings you down, okay? But yeah, we are exposed to people so much and do get sick, a lot, but sometimes, or rather most of the times, our body thwarts it off and defeats it. And then every once in a while, our body will lose that battle and you'll get a cold or a flu. Now lupus, for example, I bring up lupus because that's what's an example of what we call an autoimmune disease. And sometimes you'll get exposed to a disease where it attacks specifically your immune system. By specifically attacking your immune system, then it makes you as a whole vulnerable. Lupus starts out as attacking the body and specifically your skin, and then it can spread to other parts of the body, your blood, your kidneys and joints and so forth. It's approximated that more than 16,000 Americans, people in this country, are going to develop lupus each year. And anywhere from 500,000 to 1.5 million have eventually within their lifetime been diagnosed with lupus. We're usually diagnosed with it later in life. if not attended, it can become real serious and eventually even become fatal. It can lead to other things as well. But like I said, many people live with lupus, throughout their life. They control it, they take medication and so forth. But it is an example of what we call an autoimmune disease. And so there are some that specifically are geared toward attacking your immune system. Now here's the question that I want you to think about. You have your immune response and your inflammatory response. And your immune response is considered to be specific, where your inflammatory response is what we consider non-specific. And we'll get into those two terms in a little bit, but throughout the lecture, think about what that means, your immune versus your inflammatory, why one is specific and the other one is non-specific. All right, some things to kind of note throughout all this. Homeostasis, what it is, the function of the immune system. I think we pretty much all know what that is anyway. And the three different lines of defense that we have as part of our, what make up that umbrella term of the immune system. So what is homeostasis? Well, homeostasis basically is that ability for cells to be able to maintain a stable internal environment regardless of what's going on the outside of the cell. That basically disease tries to disrupt that homeostasis. So our immune system has a functionality for that, and that is it's a system that protects our body away from disease because our body wants to maintain homeostasis, stability. And it has what we call three lines of defense in order to have this happen. Your first line is our barriers against infection. Your second line is what we call our inflammatory response, okay? And your third is your immune response. And we'll talk more in depth about each of the three in a little bit. So, the two types of immune defense. You have two general categories for your defense mechanism. You have your non-specific, okay, that basically guards against keeping mostly everything possible out of your body. And you have your specific, which means what happens when something does manage to get into the body. Then you have your specific, and it's going to track down specific pathogens. Those two terms are kind of self-explanatory. It's pretty easy to remember. Non-specific means I'm going to keep everything out. Specific means, well, something managed to get through the non-specific, so now I'm going to track it down specifically. Your specific defenses have a flaw that when they're set to track down a specific pathogen, they can actually sometimes go right past something, a harmful agent in the body, and they'll typically ignore it because they're looking to go specifically toward that specific pathogen. And in other cases, your specific defense goes out seeking a specific response or a specific pathogen. It encounters something else and then it almost like gets sidetracked and then no longer goes out and does what it was supposed to do. So now let's talk about the three lines of defense. Your first line of defense, these are some examples. Your skin is your most obvious, it's your largest. It keeps everything, it's that membrane that keeps everything in and out of the body. So it's your protective barrier. But then you also have, for example, your mucous membrane. You have, many of you have sometimes often wondered, oh, why do we get mucus in our nose, for example? Well, that's there to keep pathogens out. It's a first line. If a pathogen in the air, a viral cell floating around in the air, you breathe it in, and it becomes attached to that wet, slimy mucus, guess where it's going to stay? It's going to stay there in your nose. And then when you clean your nose, blow your nose, and so forth, you got the pathogen out. It actually never truly entered your body and was never exposed to your bloodstream. So you keep mucus in those areas of your body, your nose, your nasal cavity, your oral cavity, around your eyes, and so forth, to keep that out. Earwax is a mucous membrane that helps to do the same thing. Your stomach acids, you could ingest a pathogen. It could be in food. You have food, you're eating in a public place, somebody happens to walk by, they sneeze into the air. They don't sneeze right on your food, obviously, but they sneeze into the air, and it floats around and it sticks to something. The food you're eating, what you're drinking, and you ingest it. Okay? Again, I'm talking about when you're out in a public place. Even at your house, and your sibling is the one that's, can have some of that, and they reach over and, get real close to you while you're at the dinner table. You're going to eat that, and you're going to swallow that pathogen, and now you're introducing it into your digestive tract. Well, your stomach acids, that hydrochloric acid, is designed to kill those pathogens, not just to assist in the breakdown of food. Sweat, tears, they contain salts and enzymes that help to kill pathogens around your eyes and across your skin as well. But like I said, eventually something does get through that first line, and so we need a second line of defense. The inflammatory response. I'll talk about that in a little bit, but a mosquito bite is a perfect example of that. No matter how good your skin is, yes, a mosquito is going to come on you one day, and he's going to bite you. He's going to, sting you, and he's going to infect you with whatever bacteria it has. So this is where your inflammatory response needs to respond. The plasma in your blood carries what we call macrophages. Remember that the prefix macro means large, and so it's going to be these large phagocytes. These phagocytes are this liquid that the plasma carries of your blood that allows your body to almost engulf bacteria, like surround it and escort it out of your body through your bloodstream, and eventually through your excretory system. The process is called phagocytosis. And then eventually the body needs to help out a little bit, because, for example, bacteria off of a cut from a metallic object or a splinter of wood and so forth and all that is not going to move throughout your body as soon as it's introduced into your body. It's not going to move very fast. But bacteria coming from a mosquito bite, for example, that's coming from a living organism. That's going to want to spread throughout your body fast, and it will. And no matter how many histamines and so forth your body releases and tries to, carry sites throughout the body doing phagocytosis, they move just a little fast, too fast for the process, and your body needs a little help. So fever is that help that's going to come in the form. Fever is that body's way of raising the temperature throughout the whole entire body. And why is that important? Why is that necessary? Because that high temperature helps to kill and slow down the bacteria. Bacteria doesn't like heat. So when your body raises the temperature, fever is good because your body is fighting infection. It's fighting bacteria. All right, so the steps of the inflammatory response. Let's talk about that one for a little bit. This picture is a great picture because it shows the whole process going on here of phagocytosis. All right, number one, you have the damaged tissue here. Now, when your skin is penetrated by, let's say, for example, the splinter of wood, the mosquito, the stinger of the bee, and so forth, you're going to have this tissue damaged. And this tissue has these histamines. And these histamines are going to be released. That increases blood flow, which is a good thing because these histamines are going to spread out throughout the site of where this occurs. Okay? Now these histamines, when they increase blood flow, that's also going to open up those slits in the capillaries, and it's going to release what we call phagocyte. The phagocyte is this clear liquid in the plasma of the blood. And what it does is it basically comes out of the capillary through these slits and comes out to where the bacteria is. And it basically starts to surround the bacteria almost like this. So it'll open up, go around the bacteria, and this will basically enclose again. And now what? Now it has basically taken in that bacteria. It will take in as many as it possibly can. Okay? And when it does so, when it has basically become engulfed or saturated with the bacterial cells, with the virus, then it's going to go back in and it's going to enter your bloodstream. When it enters your bloodstream, you will eventually, obviously, if all of this, by the way, triggers around the fourth step, triggers fever. So what do we do when we have fever? We're supposed to do what? We're supposed to increase our intake of fluids, because what that's going to do is it's going to allow your body to get rid of all this phagocyte with bacteria in it a lot faster. So like I said, you have the site of the lesion, it releases the bacteria, phagocytosis begins, the histamines are released here from the skin, they're introduced out, they increase blood flow, they activate phagocytes to come out, to diffuse out of the capillaries through these slits, they engulf the bacteria, they go back in and are introduced back into the bloodstream so that you can excrete them out of the body. Platelets in the blood are going to close up the site once all of this is taken care of. So platelets will form here to close this up, and that's basically it. Okay, all this occurs at this site. Platelets are going to also kind of build a little wall here and here, and it's going to isolate this. The body is going to isolate the temperature and raise the temperature in this area here to help kill and slow down the bacteria. And that's why after this comes out, the skin just doesn't close here, but rather you're going to get that big red bump. The red indicates the elevation of temperature. Okay? Now your third line of defense is your immune response. Your T cells and your B cells are going to do what they have to do to make antibodies so that they can fight off these pathogens. Okay? Now, T cells and B cells need one another. Your T cells are like the warrior of your white blood cells. Those are the ones that go out and attack and kill. But they need B cells because B cells are kind of like the ones that provide them with the weapon to be able to go out and fight. B cells make the antibodies, okay? And then T cells are going to duplicate and use those antibodies to fight off those pathogens, okay? This picture is a good picture. It shows it here. You have your T cell, which recognizes the virus. Now, if you look at the virus, it might be a little difficult to tell in the picture if you look closely. When you look at the very tip, at the antigen almost looks like a spherical or round-shaped structure, right? And what that does is the T cell then is going to, if you notice it here, what does it have? It has the shape of those receptors that can basically go around that roundish structure on the antigen and what? Encase it. Basically neutralize it. B cells are the ones that figure out the shape that works best against that virus. This almost happens in waves, if you would. Your body's white blood cells first attack, and that first line of attack is going to lose. But they're systematically trying to figure out what is the best way to defeat that antigen. And eventually, whether it's the third, the fourth, the fifth, the sixth wave, eventually they are. Once they do, then every B cell from that point on will make the antigen at that shape and start to provide every T cell with that antibody to be able to fight off that antigen, okay, from the viral cell, from the pathogen. So, your T cells have their receptors. Eventually they're going to find the one that it works. They go up to the infected cells. The B cells are going to be the ones that activate the antibodies that are going to fight off against that virus. And what they're going to start to do is they're going to start to attach with each other, and they're going to start to destroy the pathogens. When you remove the pathogens from the infected cell now becomes healthy again. Okay? So, antigens and antibodies, how do they kind of interact with each other? Because one basically defeats the other. The antigen is the virus's weapon, if you will, and the antibody is our white blood cells' weapon to do battle. Okay? Like it says here, they're going to bind to the pathogen's membrane proteins. They're going to cause the pathogens to basically clump together, and then that's going to weaken the pathogen's membrane to basically destroy it. Okay, for the purposes of the recording, I'm going to skip this, but I'll pause it, and I want you guys to take a second while you're watching this at home. You need to put this in numerical order. So think about everything that we discussed and try to put this in numerical order, 1 through 6, what happens first and second and third and fourth, and so forth. All right, so now let's talk about what we call active and passive immunity. And again, these two terms are going to be pretty self-explanatory as well. Your naturally acquired active immunity is going to occur when you're exposed to a live pathogen. It develops the disease and it becomes immune as a result of the primary immune response. Okay? So in other words, it's developing the memory, if you will, for it. Your passive immunity is a short-term immunization by the injected antibody. Okay? You didn't have the memory, so you were given the memory of what you're trying to fight off. Like a shot. Okay? Like taking a shot somewhere. When you're given a shot for immunity, you're given the passive form of the virus. Whereas to active immunity, you literally got the virus you contracted it from someone. Like, for example, we could be talking about chickenpox. Okay? Whereas to passive, it's going to be that shot that you get so that then your body develops the memory on how to beat the weakened form of the virus. I'm assuming we all know that when you get a shot, you're being given the actual virus. You're being given either a weakened or a dead form of the virus. Why? So that your body can attack, learn how to destroy it, and then memorize it. And from that point on, you won't get it. So your typical flu shot, for example, defends you against your 3 most popular strands of the flu that are going around that year. Why? So what it's doing is it's actually giving you a mild form of the flu, so that when you're exposed to someone who actually has one of those strands, you won't get it. Okay? All right, again, this is another class activity where you determine whether this is active or passive. So I'm going to go ahead and pause the recording here and give you time at home to be able to do it. And I just gave you the answer inadvertently to the first one. All right, so I'll pause for the whole slide. Okay, so you have your immune system in your body, but just like any system throughout your body, that system needs to change throughout your lifetime. And so your immune system needs to develop just as you grow and develop too. It needs to stay changing, in other words. It can't stay stagnant because you're going to be exposed to different things throughout your whole entire life. So how does that immune system develop? Well, once you're exposed to a particular pathogen, your immune system is going to be triggered. And your immune system is going to figure out a way to be able to beat it. And once your immune system does, then it's going to basically try to memorize that way so that when you're exposed to it afterward, you keep a record of how to beat this thing again. Now, if a person is exposed to the same pathogen again, then your immune system is going to do, again, one of two things. You have your primary antibody response and your secondary. Now, your primary response is the antibody's concentration that's going to basically peak out at about 2 weeks after being given a vaccine. Again, we're talking about being given a vaccine to trigger the response, the development of the person's immune system. Okay, after your primary response does so at about 2 weeks after your vaccination, you're going to have some time. And then now you're exposed to the actual infection. At that point, your secondary response is going to kick in. It's going to quickly rise and respond in a very intense manner. Why? Well, basically so that you don't get sick. Your concentration is going to remain at a higher level for a longer period of time until your body is able to defeat and completely, for lack of a better word, release or get rid of that virus out of your body. Okay? You take a vaccination, your primary response kicks in. It develops a memory. Sometimes when you take these vaccinations, sometimes you're going to get a little sick. Okay? Because remember, the vaccination is a weak and milder version of the illness. But then that primary response is going to develop, and that's it. Now you're good to go. And then as time goes on, when you're actually exposed to the live form of the virus, your secondary response is going to kick in. Now, if you see there on the graph, it becomes much more concentrated and much stronger. Therefore, you will get the infection in you, but you're not going to feel it. Okay? For those of you who have ever had the chickenpox, for example, you've gotten the chickenpox again. For those of you who have gotten mono at any point, you'll get mono again. But the second time around, and the third and the fourth and the 100th time around, you don't see anything because your body already understands what to do. And before anything can even show in you, your body has already defeated it and gotten rid of it. But you do get it. It's not like, for example, that chickenpox is completely eradicated out of society and you'll never be exposed to it again. It's just that, for example, you could be in an area where everyone around you has also had it, and because you've had it, it doesn't really do anything to you. Okay? Now, let's talk about what antibiotics are, and basically what helps, what ways you can help your antibiotic in doing their job. Antibiotics are drugs that are used to fight off bacterial infections. I told you that your body has its limitations as to what it can do in terms of the response. Even the first, the second, even the third line of defense, they have their limitations. What happens when even those three, and even after phagocytosis and so forth, and your specific, for example, can't track down everything inside of your body? Well, you need antibiotics. It kind of helps the process out. Plus, not to mention that your body raises the temperature to be able to kill and slow down bacteria. Well, you need antibiotics to help what? To help bring that temperature back down. And it also allows, or rather prevents, for the pathogen to not reproduce. Did I say that right? It prevents the pathogens from reproducing. So antibiotics kill off bacterial infection and stop them from reproducing. Antibiotic resistance is a problem, however. Remember, I always tell you guys, don't take an aspirin for a headache unless you absolutely have to. Why? Because eventually your body's going to become so used to it that it's going to stop working. So we call that antibiotic resistance. And it has become a problem when we tend to take antibiotics over and over and over. When you really, really need them to work, guess what? They're not going to do their job to their fullest ability. Mechanisms of evolutionary change are also involved in resistance as well. So antibiotic resistance is that form of the drug's resistance where a particular subpopulation, for example, is going to be able to fight off the antibiotics. You're going to take medicine to fight off that pathogen, and guess what? It's going to defeat it. It's going to defeat the antibiotics and not lose. Pathogenic species will become resistant to infections and antibiotic drugs. That could be a problem. And then that resistance could be intrinsic, which, it could be transmitted from person to person. And it could be acquired, where the bacteria just basically spontaneously develops a mutation, a change in its own nucleic structures, and it will allow it to fight off antibiotics. Now again, this isn't very, very, very common, but we usually see this in impoverished areas and so forth, areas where we don't have a great exposure to medicines and so forth. Here at this point as well, I'm going to pause the video here, but when you get a chance, does this also come printed out on the... Okay, so when you get a chance, you basically determine whether it's the first, the second, or the third line of defense here. All right, so going back to that question that came out in the beginning, why is the immune response considered a specific defense against pathogens, while the inflammatory response is considered non-specific? Okay? Your immune response is targeted toward pathogens that it remembers. your immune response is going to attack something, eventually, learn how to beat it, and then remember how to beat it so that it doesn't harm you again. Your memory cells are going to continue to move around. I love thinking of white blood cells as like the police of the body. So they're going to continue to patrol around your body's tissues, circulating through the bloodstream, through your cardiovascular, through your circulatory, and for very long periods of times. There are certain vaccines, for example, that have a 10-year life shelf, like the MMR, for example, that after 10 years, even the memory cells of your body will forget, and you could be susceptible to these viruses again. Your inflammatory response is going to basically, it's not specific. So it basically tries to attack everything. It can inhibit the growth of pathogens, and it basically stimulates that inflammatory response. But the thing here is to understand that it's not specific. It's going to try to do that against everything that it recognizes as foreign to the body. Whereas with your immune response, it's keeping memory of what it has already attacked. And yeah, it still tries to attack everything that's foreign, but it already develops a memory of how to do certain things. Whereas to your inflammatory response, it doesn't look for a memory. It just simply goes out and attacks everything non-specific. Okay? These questions, you can go ahead and go through. Or do they come out printed on the thing as well? So you already know what the answers are, but take a second when you get a chance to go through these questions as well. And that is basically our immune system.